Hey guys, and welcome to this video on using the two-point form of the linear equation. So let's get to it. Alright, in this video, we're going to discuss how to use the two-point form of a linear equation to model some real-world situations. So for instance, every month your energy bill depends on how much energy you use. The unit used to measure the energy you consume is kilowatt hours, abbreviated as kWh. 1 month, when you use 315 kilowatt hours of energy, your total cost was $90. During another month, you used 360 kilowatt hours of energy, and the cost was $99. Okay, first things first, we got to define some variables. Let's let our dependent variable be the total cost in US dollars, and let's give that the variable name P. Let's let the independent variable be the number of kilowatt hours you used, and let's use N for that. So note, in this case, all of our ordered pairs are going to be able to form N, P, or kilowatt hours, cost. Alright, and my claim is that from the information we have, we can come up with two ordered pairs about how much energy we use and how much it cost. When we used 315 kilowatts of energy, the cost was $90. That gives us the ordered pair 315, 90. When we used 360 kilowatts of energy, the cost was $99. That gives us the ordered pair 360, 99. So now that we've got two ordered pairs, that's all we need in order to find the slope for our linear equation and to create the entire equation to model this situation. Let's start by finding the slope. Alright, so we find our slope to be 1/5. One thing to note, we're not dealing with x and y here, so we got to make sure that in the top of our fraction when finding the slope, we have our dependent variable, in this case p, and in the denominator, we've got our independent variable, in this case n. Once we determine what our dependent variable is going to be and what our independent variable is going to be, we have to make sure to be very consistent throughout. Okay, well what does this slope of 1/5 mean? Well, it means a 5-unit increase in the number of kilowatt hours used will result in a $1 increase in the cost. Similarly, you can think of 1/5 as, for every 1 unit increase in the number of kilowatt hours used, there's a 1/5 increase in the cost, or a 20-cent increase in the cost. That is, every kilowatt hour costs 20 cents, a fifth of a dollar. Now that we have this slope, we can use either of the ordered pairs we have to create an equation in point-slope form. Now that we've got an equation, if we're told a number of kilowatt hours, we can go ahead and substitute that in for N and solve for P to find out how much that'll cost. Or, if we're told a cost, we can substitute that in for P and solve for N to find out how many kilowatt hours would cost that much. Of course, for either of these equations, if we put it in a slope-intercept form, we would get the same exact equation. And when we do so, we get P equals 27 plus 1/5 N. And what does this P-intercept of 27 mean? Well, it means that when N equals 0, or when you use no kilowatt hours of energy, the cost is $27. That is, $27 is like the flat monthly fee you pay before you even use any energy. And then each kilowatt hour of energy costs 20 cents. So every 5 kilowatt hours you use, it'll cost $1 more. In 2007, the federal minimum wage was $5.85 an hour. In 2009, it had risen to $7.25 an hour. Let us assume that the federal minimum wage has and will continue to grow at a constant rate. Now note that this is actually a really big part of our modeling situation. We're assuming that the federal minimum wage grows at the same rate, that it grows linearly. And that's why it's going to be okay for us to use a linear equation to model this situation. Of course, first things first, let's define our variables. Let's let our independent variable be the year, and we'll give that the variable N. And let's let our dependent variable be the minimum wage, which we'll call W. So in this case, all our ordered pairs will be able to form N, W, or year, minimum wage. Alright, and my claim is that from the information we're given, we can create two ordered pairs about the year and what the federal minimum wage was in that year. In 2007, the federal minimum wage was $5.85. So we get the ordered pair 2007, 585. And in the year 2009, this minimum wage was $7.25. So we've got the ordered pair 2009, $7.25. Now that we've got two ordered pairs, we can go ahead and find the slope for our linear equation. All right, so we found our slope to be 0.7 or 7/10. But what does this mean? What does the slope of 0.7 or 7/10 mean? Well, it means that every year that goes by, the minimum wage goes up on average 70 cents, which is 7/10 of a dollar. Or if we think about this fraction, every 10 years that goes by, the minimum wage goes up by $7. Of course, that's exactly what happens when you multiply 70 cents per year by 10 years. All right, now that we've got the slope of our linear equation, we can use either of these ordered pairs and that slope to create an equation using point-slope form. All right, so we've got our two equations to model this situation. Note, in this case, I don't think it's going to be as helpful to put either of these equations in a slope-intercept form. Why? Note that the intercept happens when the independent variable is 0. Or in this case, our independent variable is the year. So we're talking about the year 0. I mean, we're talking about birth of Christ here. So when we're using the year as one of our variables, and probably our independent variable, it's probably not going to be the best choice to put these in a slope-intercept form, because rarely are our models going to actually apply all the way back to the birth of Christ in year 0. I like this one in orange. It says, listen, the minimum wage was $5.85 in 2007, and it grew at an average rate of 70 cents a year. Or the one in blue says, the minimum wage was $7.25 in 2009, and of course, it continued to grow at about 70 cents a year. All right, let's try another. You're considering getting yourself a pay-as-you-go cell phone, so you ask some of your friends who have them about the costs. The plan has a flat monthly fee that includes unlimited calling and texting, but you have to pay for whatever data you use. One friend said that she used 3.2 gigabytes of data, and her bill for the month was $51. Another friend said he used 4.7 gigs of data, and his bill for the month was $58.50. All right, first things first, we got to define our variables. Let's let the independent variable be our data usage, and we're going to measure this in gigabytes, and we'll call that N. And let's let our dependent variable be the cost, and we'll call that P. So, all of our ordered pairs in this case will be of the form N, P, or data usage, cost. All right, well, my claim is we have enough information from the text to find two ordered pairs of information about how much data was used and what the cost is for that amount of data. So for instance, one friend used 3.2 gigabytes of data, and the bill was $51. So that gives us the ordered pair 3.2, 51. And when another friend used 4.7 gigs of data, the cost was $58.50. So that gives us the ordered pair 4.7, $58.50. All right, now we've got our ordered pairs. We're good to go. Let's go ahead and find the slope for this linear equation. All right, so we got a pretty nice slope, 5. But what does that slope mean in this case? That slope of 5 means that for every extra gigabyte of data you use, the cost goes up $5. That is, each gigabyte of data costs $5. All right, now that we got our slope, now that we got some points, we can use either of these points and that slope to create our equation, modeling the relationship between how much data you use and cost, using an equation in point-slope form. All right, so we've got multiple forms of the same equation for all the equations in orange and all the equations in blue. Of course, when we put them in a slope-intercept form, we get the exact same equation. And for any of these equations, if we're given some data usage, we can substitute that in for n, and we can solve for p to figure out how much it would cost. Or, if we're given a cost, we can substitute that in for p, and then solve for n to figure out how much data we could use for that cost. If we look at the slope-intercept form of this equation, that $35 is our p-intercept. That's the cost when n equals 0. That's how much it costs before you use any data. That's the flat fee that we were talking about. So that unlimited calling and texting comes at a flat fee of $35, and of course it's $5 for every gigabyte of data thereafter. Alright, last example. In 1990, the population of the United States was 250 million people. In 1996, it was 270 million people. Let's assume that the population of the United States grows at a constant rate. Again, that's a huge assumption. That's the assumption that's going to let us model this using a linear equation. Of course, is a linear equation always going to be the best way to model things? Probably not, but maybe it'll help at least a little bit. Okay, first things first, let's define our variables. Let's let the independent variable be the year, y. Let's let the dependent variable be the population of the United States in millions, and we'll call that n. Alright, so that means that all our ordered pairs will be of the form y, n, or year, millions of people. Alright, so my claim is that from the information, we've got two ordered pairs of data telling us a year and what the population was in that year. In 1990, the population of the United States was 250 million people. So that gives us the ordered pair 1990, 250. In 1996, the population was 270 million people. So that gives us the ordered pair 1996, 270. Alright, now we've got two ordered pairs, we're ready to find the slope of our linear equation. So let's go do it. Alright, one thing to note that in this example, we used y to be a variable representing a quantity that was actually our independent quantity. Usually whenever we see a y, we assume, boom, that's our dependent variable. In this case, y was actually our independent variable. So once again, it's so important when you're finding the slope to make sure that whatever variable you're using to be your dependent variable is in your numerator, and whatever variable you're using to be your independent variable is in the denominator, even if it's a y. Okay, so we found our slope to be 10/3, but what does 10/3 mean with regard to years and the population? Well, it means that every 3 years that go by, for a 3-unit increase in y, we'll have 10 million more people. There'll be a 10-unit increase in n. So that's what the 10/3 means. Every 3 years that goes by, there'll be 10 million more people. Every 3 that y goes up, n will go up by 10. Alright, now that we've got a slope, we can use either of these ordered pairs to model this situation using a linear equation in point-slope form. Awesome. Now note in this case, our independent variable represents the year again. So when our independent variable is the year, it's probably not going to make much sense to put this equation in a slope-intercept form, because the intercept would be the population in the year 0. Once again, talking about the birth of Christ here. So when this is the case, and it doesn't really make sense to put these in a slope-intercept form, this is the form of the equation I like the most. Why? Because it really tells a nice story, and it's pretty easy to interpret. For the one in orange, in the year 1990, the population was 250 million, and it grew at a rate of 10 million people every 3 years. Or for the one in blue, in 1996, the population was 270 million, and of course, it grew at a rate of 10 million people every 3 years. Again, now that we have an equation, if we're told a year, we can substitute that in for y in either of our equations and solve for n, and find the population in that year. Or, if we're given a population, we can substitute that in for n and solve for y to figure out in what year that would be the population. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.